Let's start with something we already had on the table in the last couple of days for those of you who are on the ship. A distinction commonly drawn between two views of time. And as you see, I've stolen these pictures from the Scientific American. On the left, we have the what's supposed to be the intuitive view of time. We have, I'll say a little bit more about the ingredients of that in a moment. On the right, what's supposed to be the view of time given to us by physics. In what's supposed to be the folk ordinary view of time, the dynamic or passage view as it's sometimes called, we can distinguish several elements. And I think it's helpful in thinking about these things to keep these elements distinct, because I think in principle one could have a view of time which had pretty much any combination of the three without the others. So there's the idea that you have a distinguished present moment, shown in this picture by the black rectangle containing the Earth and the Moon. You have the idea that there's some kind of something dynamic in the picture, an objective flow of time, what's sometimes called becoming. I'm going to be talking about Eddington, who was particularly keen on that word. And then there's an objective direction of time. So in some deep physical sense, one end of this picture is the past, the other end is the future. It's said to be a minority view among physicists, but it has and still has these days some distinguished champions. The opposing view, said to be the majority view among physicists, regards time as simply one dimension in a four-dimensional block, and rejects all three of those elements I distinguished before, which it treats as just subjective aspects of time. And I'm going to start by giving you some remarks from famous physicists and mathematicians illustrating their rejection of each of those three elements. So here's Einstein with his old friend Besso. Tim Maudlin had this quote yesterday, but Tim was interpreting it as a rejection of a direction of time. I think it's perhaps better read, especially seen in context as from a letter to the Breed family of Besso, as rejecting the idea that there's something distinguished about the present moment. Einstein says, "For we convinced physicists, the distinction between past, present, and future is only an illusion, albeit a persistent one." And it's easy to see how that can be a comforting thought. The thought is that the lost loved ones still exist, as it were, they're just not present to us. But that's no deeper a matter than it would be if they were not present in this room, but were present somewhere else. Here's Hermann Weyl rejecting the idea of an objective flow of time. Again, a famous passage. Weyl says, "The objective world simply is, it does not happen. Only to the gaze of my consciousness crawling upward along the lifeline of my body does a section of this world come to life as a fleeting image in space, which continuously changes in time." Okay, so that's the second element, the idea of objective passage or flow. Oh, and I just, if I've got time, I'll just stick in here a quick word from the poets on this subject. This is a minor English poet called Austin Dobson from the 19th century, who says, "Time goes, you say. I know, alas, time stays. We go. Ours is the eyes deceit of men whose flying feet lead through some landscape low. We pass and think we see the earth's fixed surface flee. Alas, time stays. We go." It's a sort of a nice expression of this view that there's something illusory about the passage of time. Given that I'm so short of time, I can't resist putting in another little snippet of Dobson. This is from a poem called "On the Hurry of This Time," a lament about the pace of modern life, written in 1885. It says, "With slower pen men used to write of old when letters were polite. They knew not steam. Electric light not yet had dazed their calmer sight. Too swiftly now the hours take flight. What's red at morn is dead at night." Isn't it wonderful to learn that people were having that thought in the late 19th century? Little did they know what was coming. Okay, so back to the physicist now. So here's another famous passage from Boltzmann, in which Boltzmann is rejecting the idea that there's an objective direction to time. And what he's doing is considering a hypothesis about why entropy might be so low in the past. And it's the hypothesis that in an infinite universe, fluctuations producing extremely low entropy are inevitable, although extremely rare. And the diagram here is supposed to represent very crudely the entropy history of the universe as a whole, and here's one of these very large fluctuations. Boltzmann says, in the universe, which is in thermal equilibrium throughout and therefore dead, there will occur here and there relatively small regions of the same size as our galaxy, which fluctuate noticeably from thermal equilibrium, and indeed the state probability in such cases will be equally likely to increase or decrease. And then this is the bit I want. For the universe, the two directions of time are indistinguishable. Just as in space, there's no up and down. However, just as at a particular point on the Earth's surface we call down the direction towards the center of the Earth, so will a living being in a particular time interval of a single world distinguish the direction of time towards the less probable state from the opposite direction, the former towards the past, the latter towards the future. So Eddington is saying that creatures living there will think of the future as being to the left, creatures living here at A will think of the future as being to the right, and there's no sense in which one of them gets it right and one of them gets it wrong. Okay, so what you've just seen are some famous physicists giving us the three ingredients which go into the rejection of the folk view of time, the endorsement of the so-called block universe or static view of time. Now to Eddington. I mentioned that there are some distinguished physicists who reject the block view, and one of the first of those was Sir Arthur Eddington. Here he is with Einstein and Ehrenfest, Lorentz and de Sitter. When I was Googling for pictures of Eddington, I came across this one, and as a Doctor Who fan, it was so striking to see Doctor Who standing next to Einstein in this way that I had to put it into the talk. Here he is on the cover of Time magazine in 1934 on the occasion of a visit to America. This is an indication of what a public figure he was at this stage. Eddington was one of the great scientific popularizers of his day. The caption under the picture, you probably can't read it there, but it's what I have at the top. His universe expanded into popularity. And I found that on the Time website, there's an archive, you can look at the articles which go with the pictures on the cover, and this is the one about Eddington. So Sir Arthur had slipped into the US from SS Britannic when she touched at Boston last fortnight. I thought it would be nice to have a picture of the SS Britannic to put in the talk too, especially since we've just been on a ship. So here's the SS Britannic in service as a hospital ship in the First World War. She's actually a sister ship of the Titanic. Unfortunately, she was no more lucky than the Titanic. The Titanic ran into an iceberg, the Britannic ran into a mine in the Aegean and suffered the same fate. It was a rather unlucky family. So obviously that couldn't be the ship on which Eddington went to America in 1934, so what was it? I think it must have been this one, which looks very much like the National Geographic Explorer, doesn't it? This is the MV Britannic, the motor vessel Britannic, the next ship to bear that name. Then the article goes on for a day or two. No one, not even his Manhattan publishers, seemed to know where Sir Arthur was. Then he had stepped off the 20th Century Limited in Chicago, gone straight to a new dormitory at the south edge of the university campus with his 3 well-worn suitcases. So I was getting engrossed in this story by now, and I thought, well, perhaps I can find a picture of a train. And I found this. This is a train which many train enthusiasts regard as the most beautiful train ever made. I'm cheating a little bit because when Eddington travelled on this train, it was an earlier model. This one wasn't introduced till a couple of years later. But then I thought, well, look, we're talking about flow and passage and thermodynamics. Let's take this a bit further. So if this works, let's see. Isn't that great? It's wonderful what you can find on YouTube these days. Okay, now, for some reason. Sorry, this isn't working. That's what I want. Okay, so this is Eddington's book, The Nature of the Physical World, from 1927. And this is the place, it seems, in which the phrase time's arrow first comes into the scientific literature, especially the popular scientific literature. And here's the passage. I don't know if you can see it from back there. Eddington says, "The great thing about time is that it goes on, but this is an aspect of it which the physicist sometimes seems inclined to neglect. In the four-dimensional world considered in the last chapter, the events past, and present and future lay spread out before us as in a map." It's the block view. "The events are there in their proper spatial and temporal relation, but there's no indication that they undergo what has been described as the formality of taking place, and the question of their doing or undoing does not arise. We see in the map the path from past to future or from future to past, but there's no signpost to indicate that it's a one-way street. Something must be added to the geometrical conception comprised in Minkowski's world before it becomes a complete picture of the world as we know it." So this is, as you see, this is an expression of the view that there's something missing in physics, something corresponding to the passage of time, to becoming. And Eddington thinks that has to be in some way related to thermodynamics. He says the second law of thermodynamics opens up a new province of knowledge, the study of organization, and it's in connection with organization that time flow and a distinction between doing and undoing appear for the first time. And he says that unless, this is I think, a fascinating passage for a physicist to be writing, unless we've been altogether misreading the significance of the world outside us by interpreting it in terms of evolution and progress instead of static extension, we must regard the feeling of becoming as a true mental insight into the physical condition that determines it. So what the idea he's expressing is that in our conscious experience, we're aware of a fundamental feature of reality which is otherwise missing from physics. So physical instruments can't tell us about it, but our consciousness knows about it. He says, the view here advocated is tantamount to an admission that consciousness, looking out through a private door, can learn by direct insight an underlying character of the world which physical measurements do not betray. Now, Eddington is a very thoughtful and good physicist, and he's aware of what a sort of controversial view he's expressing here. And so he goes on to say, the physicist does not look kindly on private doors through which all sorts of superstitious fancy might enter unchecked. But he says, well, what's the alternative? And what he does at that point is to issue a challenge to his opponents. And his challenge is something that I think should be better known today. And that's really the message of this talk. He says, is he, that's the physicist who renounces the private doors, ready to forego that knowledge of the going on of time which has reached us through the door and content himself with the time inferred from sense impressions, which is emaciated of all dynamic quality? No doubt some will reply that they are content. To these I would say, then show your good faith by reversing the dynamic quality of time, which you may freely do if it has no importance in nature. And just for a change, give us a picture of the universe passing from the more random to the less random state. And then he elaborates that a bit. I'm a little bit short of time, so I won't read out those passages. I'll just read the conclusion. He says, if you genuinely believe that a contra-evolutionary theory is just as true and as significant as an evolutionary theory, surely it's time that a protest should be made against the entirely one-sided version currently taught. And I think he's right. It is time, and was time then, and it's certainly time now, that some kind of a protest should be made. Perhaps not a very loud protest, but an awareness that the one-sided way of telling the story might not be the only one we need. Okay, so let's think about what would be involved in doing that, in meeting Eddington's challenge. And I think the first obvious step, is to remember Boltzmann on up and down. Suppose someone were to challenge the idea that up and down are not objective directions in the universe. Someone might say, well, if you think up and down is not objective, just try living your life the other way up, standing on your head. That would be crazy. Now, of course, the answer, as we know, is, well, we can't do it around here, but if we go somewhere else, around the other side of the planet, then it's quite easy, as I can attest, to live your life with your head pointing in the opposite direction. Okay, so perhaps something like that will work in the temporal case too. So let's distinguish three cases. The case of around here, I'll say a little bit more in a moment by what I mean by here in that context, the very big and the very small. And here's a picture which I've just borrowed. I actually found this in a Norwegian airport a couple of years ago. Norway is a small country, but it likes to have an accurate conception of its own place in the universe. So this, I don't know if you can see this says here. It's an indication of where Norway is. I'm just using I'm just using this as a kind of crude. A sort of crude illustration of the sort of ordinary macroscopic scale up to the scale of galaxies and clusters of galaxies, and in effect up to the scale of the observable universe. So that's what I mean by around here. Now, in this region, very broadly construed, we know that physics is dominated by special initial conditions. We've heard quite a bit about that in the last couple of days. And in this region, Eddington is right. Randomness only works in one direction, and we can be more precise about what that means than we could in Eddington's day. And the real puzzle, if there is one, not everyone agrees that this is a puzzle, but the real puzzle, if there is one, is why it doesn't work towards the past. And the answer to that question seems to lie in cosmology, and we're going to be hearing more about the particular sort of cosmological story later in this session. But it's interesting that Eddington himself was onto the idea that that's where we should be looking. He says, this is an article from Nature in 1931, "We are thus driven to admit anti-chance," that equivalently something like low entropy, a low entropy boundary condition. And apparently the best thing we can do with it is to sweep it up into a heap at the beginning of time. Okay, so that's around here in the broad sense that I mentioned. But that leaves two other scales to consider: above the anomaly at larger scales, and below the anomaly at smaller scales. Okay, so above the anomaly, what we seem to know already is that the asymmetry in our region is widely believed to stem from special initial conditions around the time of the Big Bang. But if we're interested in questions like, well, why those initial conditions? Are they generic if the Big Bang is not unique? If we want to ask questions like these, we shouldn't assume that the physics we need obeys the same kind of asymmetry. That would clearly be an unjustified extrapolation from our own local neighborhood. Remember again Boltzmann, past and future may be just like up and down. So to give you an example of the kind of thinking which would be the kind of thinking which would avoid that mistake, I'm going to give you a picture which I stole in this case from Sean, from one of his talks I found online, I think. Here's a description of a slightly more detailed version of the same picture from one of his papers. The point I want to emphasize about this sort of cosmological model is the one that Sean himself expresses like this. He says, so perhaps our observable universe is just a tiny part of a much larger ensemble that is overall time symmetric. So if we want to think about cosmological models of that kind on the large scale, then the idea that there's a preferred temporal direction in the model as a whole has simply disappeared. Temporal directions have become local matters in the way that up and down are local matters on the surface of the Earth. So what's happened to Eddington's challenge there? Well, clearly it's been met in the sense that a proposal has been made about a way of doing physics which doesn't distinguish between the two directions at that scale. Okay, so let's move now to the other side, to what I call below the anomaly. The familiar asymmetry that we're used to, the asymmetries associated with the second law of thermodynamics, have a kind of statistical character to them. But at some point, if we look at systems with smaller and smaller numbers of ingredients, we expect to get down to a substatistical level. And we should be careful about unjustified extrapolation of the familiar time asymmetries to that level too. Again, this is something that Eddington himself was already onto. There's another quote from the same paper in Nature in 1931. Eddington says, when Dirac's theory is applied to 4 particles alone in the universe, the analysis very properly brings out the fact that in such a system there could be no steady one-way direction of time, and vagaries would occur which are guarded against in our actual universe of about 10 to the 79th particles. One of Eddington's party tricks was calculating the number of particles in the universe, and journalists used to enjoy asking him about that, and he would say something like, I can't quite remember the exact figure, but I think the last digit is a 6. Okay, so here's a little puzzle about quantum mechanics. It's something I found puzzling for a long time. Quantum mechanics assumes that the state of a quantum particle, or photon in this case, depends on past measurements performed on the photon, but not on future measurements. So I've tried to represent that here by, here's the photon moving from left to right. Its state here is correlated with the orientation of a polarizer in its past, but not with the orientation of a polarizer in its future. Now, okay, yeah, and so the point is that the opposite thing, where we have the photon now moving from right to left, where its state is correlated with the polarizer in the future, not the polarizer in the past, that's normally thought to be disallowed. So we've got some kind of temporal asymmetry there. Now, it's conceivable that in some sense that could be statistical asymmetry or related to the second law of thermodynamics. But most people assume that the same kind of asymmetry is going to be there, as it were, all the way down. So even if we're in the project of looking for hidden variable models of quantum mechanics, we're still entitled to assume that same asymmetry, that we're still entitled to assume that the state of a quantum particle can't depend on what happens to it in the immediate future. And that's an assumption which slips in, often almost unnoticed, into all these standard so-called proofs that there can be no hidden variables, or at least no local hidden variables. I mean, it's there in Bell's theorem. It's the assumption that the hidden variables, any hidden variables in the picture must be independent of future measurement settings. So the question I just want to leave on the table is the possibility that that too might be an unjustified extrapolation from the familiar time asymmetry in our neighborhood at ordinary scales. And if that did turn out to be the case, then it would turn out that there'd be a sense in which we'd been missing something very big indeed by not facing up to Eddington's challenge, that is, by not thinking about the question as to how far we're justified in extending the ordinary time asymmetric pattern of explanation that we use in physics. There's a couple of recent papers of mine which discuss some of those issues. Okay, so just to finish up, why does all of this matter? I think it matters because the project that we're engaged in here in the case of time, that is the project of distinguishing what's objective, what's really out there in the world, from what's subjective, that is, from what in some sense comes from us, is one of the defining projects of physics and philosophy, and has been since the time in the 17th century when they more or less diverged. I think that in the case of time, the distinction itself is still very much in flux. We haven't agreed on what's subjective and what comes from us, and that's evident from our discussions over the last couple of days. I think that it's helpful to distinguish what the key ingredients we're talking about, and as I said at the beginning, I think there are three key ingredients: the question of direction, the question of flow, and the question of the status of the now. And in my view, physics is still kind of in transition on these issues. It's mostly committed to the view that these are not objective features of reality, though there's still lively debate going on some of those points. But even among the community within physics who pay lip service to the idea that these are not objective features, I think people haven't quite absorbed the consequences of that. So people haven't got used to thinking in the way that's appropriate if you think those things are merely subjective. And I think that Eddington himself made the wrong call in thinking that physics was leaving something out in not being able to tell us anything about becoming. So I think in that sense he made the wrong call. But his map, and I think that his map of the terrain needs some work. I mean, he himself doesn't properly distinguish the notion of flow from the notion of direction, for example. But despite all that, I think that it's fair to say that he himself saw what was at stake with a kind of clarity which has rarely been matched. And so I think it's fair to pay some attention to Eddington in the context of these kinds of discussions. So I'll leave you again with Eddington on the cover of Time magazine. Here's the quote at the bottom is from Eddington's obituary in Time in 1944. Time says, one of mankind's most reassuring cosmic thinkers. He says he discoursed on his cosmic subject with a wit and clarity rare among scientists. I don't really know whether to feel more offended by the suggestion that is rare, that is rare among scientists, or by the implicit suggestion that it's more common elsewhere. I think okay, that's all I have to say. Thank you.